SZ on an up. So an up would be 1, 0. Has to equal what?
H bar. Number 2 times
HR.
MS.
Yeah. How about if I wrote it, it has to equal H bar MS 1, 0. And what is the projection of angular momentum for an up? It's a half. So that equals H bar over 2, 1, 0. And I can build this by going SZ on 0, 1 equals H bar MS 0, 1. Or this is an up, and then this is a down. So that equals, in this case, it equals
Negative H bar.
minus H bar over 2. And then 0, 1.
Thanks.
All right? So when you go through and you do it the same way, what you end up with is the following, is that SZ equals H bar over 2, 1, 0, 0 minus 1. Okay? You can go on to build SX, again, in a Z basis. So this is all on a Z basis. And SX in a Z basis equals H bar over 2, H bar over 2, 0, 1, 1, 0. And then SY in a Z basis equals H bar over 2, 0, and then there's an I here, sorry, 0 minus I, 0.
Because when you square, you get back to the.
Okay. So guys, how about these operators? Are these operators Hermitian or are they not Hermitian?
They're Hermitian.
They are H.
All of it, even the
Yes,
Z,
yeah,
even the
right.
Y one?
Yes,
Well,
C
because
is
if you
covered.
square it, you get +1 and -1.
They're all Hermitian because you got to look at the transpose complex conjugate. All right, so even this one is. So what does that mean about calculating expectation values using those operators?
They give you observables.
They give you observables, they give you real numbers, just as they should. Okay?
That's the.
All right, but check this out. If you want, I've seen it like this. Sigma vector matrix in a Z basis. All right, so this is the 3 vector components of the matrix equals, essentially, ready? Equals sigma x, sigma y, sigma z, where sigma x is this thing, and sigma y is this matrix, and sigma z is this matrix. So that if you wanted, you could do this. This is crazy notation.
Sigma X is SC.
So watch. See if this makes sense. And this is crazy notation. I don't know anybody that uses anything like this, all right? Okay, so here's what the scoop is. Here you have SZ, that's a Z component of spin operator. Here's SX, the X component of the spin operator. Here's SY, the Y component. That's kind of like a vector, right? So when I combine all those things together, I call it S operators, but vectors. So it's all three of them. Right? All three of them? Okay, and what I say is it equals h bar over 2 times this vector of 3 matrices. So this vector matrix is our 3 separate matrices. The x component, this one, the y component, that one, and the z component. And so the spin is just h bar times this thing. You see that? Find that?
Yep.
My notation completely makes sense to me. I'm not sure.
Yeah, because you just factor up h bar over 2.
Right, and then I'm kind of let it equal a matrix. Let it equal the vector. I'm combining these components, matrices, into a total vector. This is the x and the y and the z component. This is sx, xy, z, xy, z is a vector. So I'm going to call that vector S matrices with a vector. The x, y, and z components. And it equals h bar over 2 times this vector, and this vector is that component, that component, that component. All right? So the big scoop is this thing is called the Pauli spin matrix. And if you want, these are called the Pauli spin matrices.
Which one's the polyspin matrix, the big one?
So, I'm inventing this here, Matt. These are called the Pauli spin matrices. When you put those matrix components together, there's an x component, a y, and a z component.
Yep.
I'm calling that all together the Pauli spin matrix, the Pauli spin matrix vector. All three of them together. Right? That's it.
By finding the spin in Z, you get the matrix in X. The spin in X is the matrix in Y, and the spin in Y is the matrix in Z.
Look, if I made this too complicated, then ignore it and just use the book's definition.
No,
Okay?
Just keep it
Makes sense.
separate.
I'm trying to make
Okay.
sure when I'm putting down to the X is Z, Y is X, Z is...
Oh, yeah, I screwed up. I see what you're saying. The X part is way...
SX is in the middle.
This is XZ, this is SX.
Right.
And all on a Z basis. So this is the SX.
Yeah, I think you're
There.
That's what I was trying to figure out is,
Yep, no, I screwed up. And then the Y one is over here.
so this spin is the actual spin with the
Yeah.
different ones around. That's what I was trying to figure out is
So,
Okay, so look, guys.